Hi everyone, this presentation covers Chapter 14, Correlational Studies, in the third edition of Jacobsen's textbook, Introduction to Health Research Methods, a Practical Guide. In this chapter, you will learn that a correlational, ecological, or aggregate study uses population-level data to examine relationships between exposure rates and disease rates. Here's an outline of the chapter. Section 14.1 provides an overview. Section 14.2 covers aggregate data. Section 14.3 covers avoiding the ecological fallacy. Section 14.4 covers some correlation topics, and Section 14.5 covers age standardization. Section 14.1 Overview. So in this chapter you will learn that a correlational study uses population-level data to look for associations between two or more characteristics that have been measured in several groups. Variables included in correlational analyses are usually aggregate or at a group level. So this could be a proportion of a population with a particular characteristic, say an exposure or disease, or an average value of a variable in the population, which could be, say, age. Sometimes, correlational studies are called an aggregate study because correlational studies look only at group-level population data and do not include any individual level data. So figure 14.1 goes over key characteristics of correlational studies. The objective is to compare average levels of exposure and disease in several populations. The primary study question could be something like, do populations with a higher rate of exposure have a higher rate of disease? The population includes existing population level data, but no individual participants are included, and that's the most important thing to note about this type of study design. So when would you use this approach? When the aim is to explore possible associations between an exposure and a disease using population-level data. One of the requirements of a correlational study is that the topic has not been previously explored using individual-level data. Some of the things to think about first are to 1. Select the sources of data that will be used, and 2. Decide on the variables to include in the analysis. Some things that you want to look out for, which will be discussed a little bit further, are the ecological fallacy and limited publication venues. The key statistical measure is a correlation. So one characteristic of the populations being examined in a correlational study is an exposure. Correlational studies then examine exposure outcome pairs. The statistical methods can be used to control for interactions among related variables. An ecological study is described as a correlational study that explores any sort of environmental exposure. Section 14.2 covers aggregate data. Information about all variables of interest must be available for a suitable number of populations that can be grouped as place or time in any type of correlational study. So for any one variable in a correlational study, the best option is for the data to come from the same source. But when using multiple sources of data for one variable, the researcher should establish some sort of scientifically justifiable set of inclusion criteria for the study, and then exclude any data sources that may not meet those eligibility criteria. Now, before conducting a statistical analysis of aggregate data, data from each population should be entered into some sort of a spreadsheet, and this could be manually entered, or this could be through some sort of online survey tool that is very helpful for data entry. Each population should be assigned to its own row in the spreadsheet, and each exposure and outcome should be assigned to its own column. Then the data should be filled into the cells in each column so that they line up with the correct population. So figure 14.2 gives an example of this. We have our population in the first column, and then the exposure 1 in the second column, and then the outcome in the third column. So the populations are listed as A, B, and C, and then the average numbers are listed here. Section 14.3 covers avoiding the ecological fallacy. Correlational studies compare groups rather than individuals, and this is very important and something that really needs to be noted when conducting correlational studies. No individual level data are included in the analysis. It is only population level data. So the ecological fallacy is when an incorrect assumption is made that the individuals follow the trend observed in population level data. The experiences of individuals in a population may vary significantly from the population average. Section 14.4 goes over some concepts related to correlation. A correlation is a statistical measure of the degree to which changes in the value of one variable predict changes in another value. So if you look at them on a scatter plot, each point represents one population in a study. The exposure is plotted on the x-axis, the outcome on the y-axis, and a trend line is fit to the data points to examine the best fit. Correlation can be described as strong, mild or moderate, and weak or non-existent. A strong correlation is when all the points fall neatly along or very near the slope line. So this could be a positive upward or a downward trend. A mild or moderate correlation is when all the points are not exactly linear, but a line can be drawn through them to show the trend. A weak or non-existent correlation is when the points appear to be randomly placed and no obvious line can be drawn through them, or when the best fit line is horizontal. And so here are some examples in figure 14.3. Our positive slope is letter A, our negative slope is letter B, and then you have the C there. There are two different statistical measures that are calculated for correlation. The first one is a Pearson correlation coefficient, and this is used with continuous variables and other variables with responses that can be plotted on a number line. The Spearman rank order correlation is used for ordinal variables, and these are variables that could be assigned a rank for things like a Likert scale from 1 to 5, from strongly disagree to strongly agree. The value of a correlation, either the Pearson or the row, are the same. A -1 is when all the points lie directly on a line with a negative slope, and a +1 is when all the points lie perfectly on a line with a positive slope. When the row equals 0, there is no association between the exposure and the outcome. Something else that can be looked at for correlation is a coefficient of determination, or the R-squared. This is the strength of correlation without indicating the direction of the association. So if the value is 0, then that indicates there is no correlation, and if there is a value of 1, that indicates the perfect correlation. When more than two variables are being compared, the goal may be to understand the relationship between two variables when you're adjusting or controlling for the effects of the others. Linear regression models can be used to assess associations when controlling for other variables, and the important thing to note here is that the outcome is a continuous variable for linear regression. A correlation can be present even when the relationship is not causal. So the term correlation should not be used as a synonym for causation. It can infer causation, but correlation does not necessarily equal causality. Another term that is used is association, and this is more appropriate than correlation when you're looking at categorical variables. In correlational studies, you may also use age standardization. Sometimes populations that are being compared are from very different age structures. So you may have a population that has younger groups that may have more favorable health statistics because fewer population members have developed chronic diseases yet, or they may have an older population with less favorable health statistics because of the chronic diseases that develop with age. And age adjustment is aimed to improve the validity of comparisons of two or more populations with different age distributions. So this can be done by calculating an age-specific rate. This is a rate that's particular for an age group, say 65 and older, or ages 18 to 45 years. Age standardization applies age-specific rates from one or more study populations to a standard population, or vice versa, to generate comparable rates for populations with different age structures. So an age standardization method, it really depends on how much is known about the age distribution in the study population before using this. A direct age adjustment is an age-specific rate in two or more study populations with different age structures that is compared to one standard population, so the rates in the study population are more fairly compared. So for example, the rates from several cities in the U.S. could be standardized to the national population, say from data from the U.S. Census, or the rates in several countries can be standardized to the global population. A direct age standardization can only be conducted when age-specific data are available for all of the study populations being compared. So to calculate an age-adjusted overall rate for each study population, each population's age-specific rates are applied one at a time to a standard population. The expected numbers of outcomes for each age group are then added together, and the sum is used to calculate an all ages rate in a standardized population. These are directly comparable because they are based on the age distribution in the same standard population, and they allow for a fair comparison of disease status in the two populations. And so figure 14.4 goes over a direct age adjustment in two different cities. City A includes a young population, and City B includes an old population. And here you can see how the rates are adjusted on your own time. Jacobsen also talks about indirect age adjustment. This applies age-specific rates in a standard population to a study population so that the determination can be made about whether the overall rate in the study population is greater or lesser than expected, given the population's age distribution. Indirect age standardization methods can be used to compare study populations for which the age distributions are known, but age-specific rates of exposure and/or disease are not known. Another measure is the standardized mortality ratio. This compares the number of deaths observed in a study population to the number of deaths expected in the study population based on the age-specific mortality rates in that standard population. And 14.5, so figure 14.5, goes over the indirect age adjustment. Here we have City D, which has an old population, and then it looks at the differences in mortality rate based on the standardized mortality ratio here, the observed over the expected results. When conducting statistics for age standardization rates, crude and adjusted statistics can be calculated. A crude statistic is one that is unadjusted. So say when only one population is being described, the crude statistic is often the correct measure to report because it accurately describes the true experience in the population, versus an adjusted statistic, which has been corrected to account for the effects of one or more variables. Now, this often depends on the aims of the study and not just whether or not one or more populations are being described. So figure 14.6 goes over crude and standardized rates, and it talks about the differences here in low, middle, and high income countries. So this gives you a really good example of using age standardized mortality rates. So that is it on Chapter 14 on correlational studies. Thank you for listening.